Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Line Integrals in Two Dimensions. As always, be an attentive learner as you watch this video. Line integrals. In this lecture, we define an integral that is similar to a single integral, except that instead of integrating over an interval, AB, on the real line, like this, we integrate over a curve, and the curve could be curve C. Such integrals are called line integrals, although curve integrals would perhaps be better terminology. They were invented in the early 19th century to solve problems involving fluid flow, forces, electricity, and magnetism, and are still part of your physics subjects these days. So we start with a plane curve given by some parametric equations like you studied in Calc 2. So x is equal to x of t, y is equal to y of t, and t runs from here to here. And again, the picture is t runs from here to here, and it traces out this curve as a parametric equation. So we have this, or equivalently, we have the vector equation r of t is equal to x of t in the I direction plus y of t in the j direction. And we assume for this discussion that C is a smooth curve, meaning you have continuous first derivatives, and the first derivative does not equal to 0 any place. So if we divide the parameter interval, that's the a to b, into little slices like that, so that it's ti minus 1 to ti of equal width, and if we let xi equal x of ti and y equal y of ti, then the corresponding points pi of xi, yi divide c into subarcs of length delta S1. So you see these are the sublengths that we have. So there's the first one, the second one, and so on and so forth. And these are delta S1, delta S2, and so on. There's the picture. So if we pick any point in that subarc, so we pick a point there, a point there, a point there, and so on and so forth, that corresponds to t star I, which is some point in the subinterval. And if f is a function of two variables whose domain includes the curve C, and we evaluate f at this point, xi star, yr star, and multiply by delta x of the subarc and form the sum, we get a sum that looks like this, and that's similar to a Riemann sum, and you've done this often enough that you realize we're going to take the limit of these sums and make the following definition by analogy with a single integral. But notice that this is delta S. So here's our definition. If f is defined on a smooth curve C, then the line integral is the limit as n goes to infinity of this Riemann sum, and that's the integral over the curve C, f of xy ds. And this is only if this limit exists. Now, if you think about the way we defined arc length before, the derivative of arc length, since the arc length was equal to this integral, then this integral, if we do ds, then it's going to be equal to, well, ds dt is equal to this. So that means ds is equal to this factor, the square root of dx dt whole squared plus dy dt whole squared, and the square root of all that times dt. So that is an arc length factor that is there, and so we will have this saying the same thing I just said. So we have an equation for evaluating this. Now, in the special case where C is just a line segment joining A and B, it reduces to the integral that we know, where the y is just y equals 0. So line integral is, in fact, a generalization of the ordinary integral, and in fact reduces to the ordinary integral in this case. Okay. So just as an ordinary single integral, we can interpret the line integral of a positive function as the area. In fact, if f of x, y is greater than 0, then this line integral over the curve C, f of x, y ds, represents the area of one side of the fence or curtain in this figure. So you see here's the curve. Your f of x, y is greater than 0, so it is this area. Now notice that this does have the curved part though, so that is a simpler, not a simpler, it's actually a more complex situation. So this is what we're representing. This is a geometrical interpretation. Okay, so when would you use this? Well, line integrals can be used to determine many important physical quantities, such as meteorologists can use line integrals to measure circulation around a closed curve. So that's just the circular flow of the wind path of a hurricane or a tornado. So these things go in circles, or not circles, but curves like that. An electronics manufacturer can use line integrals to find the surface area of a curved TV screen in order to determine the exact amount of glass needed for the screen. This information can be used to determine the exact cost of manufacturing the screen. And a surveyor can use line integrals to determine the average elevation of a winding downhill road. So this goes down, it curves, and so on and so forth. Let's now do a problem. So please evaluate over the curve C 2 plus x squared y ds, and C is the upper half of the unit circle x squared plus y squared equals 1. You know what to do. Let's see how you did. So the first thing we have to do is parameterize C, and we know from previous discussions, I think in Calc 2 and a little bit in Calc 3, that this is a good parameterization. So this is x is equal to cosine t and y is equal to sine t. Now, this parametric representation, just as a look ahead, starts here and goes this way. So really we should have, or I should have said, that this is going counterclockwise, because you see, and we'll see this later, you'll get a different thing if you're going clockwise, and that would be a different parameterization. So let's do the calculation then. So the line integral over C of 2 plus x squared y ds is equal to, now I plug in this, so everywhere I have x, I put cosine of t, and everywhere I put y, I put sine of t. And I know that I'm going from here to here, so I'm going from 0 to pi. And then ds is the square root of dx dt whole squared plus dy dt whole squared, square root of that dt. So I plug that in, and then dx dt is going to be sine of t. Actually, it's going to be minus sine of t, but when I square it, I get, well, sine of t squared, and cosine squared of t. And you see, in this case, this factor becomes just 1. So now I'm going to be forming this integral. Again, make sure you follow these calculations, because I will be asking you to compute things like this. So you use a fundamental theorem of calculus, you're using U substitutions and so on and so forth, evaluating at pi and 0, and you get this as your final answer. So it is 2 pi plus 2/3. That's the exact answer. Now, suppose that C is a piecewise curve and it's a union of a finite number of smooth curves. So in fact, you're doing this way. So you're going along this curve, but then it has a different parameterization, another parameterization, another parameterization, and another parameterization. Well, this, by the same theory that we talked about before, the integral over the curve is, I just integrated over the subtending curves. Let's do that for this problem. So the problem here is evaluate over the curve C, the line integral 2x, and this is ds, where C consists of the arc C1 of the parabola y equals x squared from 0, 0 to 1, 1, followed by the vertical line segment from 1, 1 to 1, 2. Your first step, of course, is going to be drawing this, but I think you knew that, and then finding a parameterization. You know what to do. Let's see how you did. Well, first we parameterize it along the parabolic arc, and the easiest way to do that is let x equal x and y equal x squared from 0 to 1. And you see I will go along this curve. So now over C1 then I have, this is 2x ds is, as always, this factor. Now this is just dx because I'm using x as the parameter. And so we go from 0 to 1 now. This is going to be, when I take the derivative of this, I just get 1, so 1 squared is 1. When I take the derivative of this, I get 2x, and when you square 2x, you get 4x squared. So this is what I have. I can do a u substitution to evaluate this integral. And it is not difficult. You should make sure you get this, but the answer is, exact answer is, and this is the kind of question that I might ask you on a test or something someday, 5 square root of 5 minus 1 over 6. Now that's not the final answer, but that's the answer for this part of it. Now we need to evaluate over C2. Now on C2, we'll choose x to be 1 because x is always 1 on there, and y is just going to be y, but y will run from 1 to 2. So now we make that substitution. This is going to be 2 times 1. And this is just going to be, let's see, the derivative of 1 is 0. And this derivative is 1, so that it really is just 1, so I get 2. So the total integral is the sum of the integrals over the two curves that comprise C. So you get this number plus this number, which is 2. That is the exact answer. Now, any physical interpretation of a line integral depends on the physical interpretation of the function f. But suppose this rho of xy, which is going to play the role of f here, represents the linear density at a point, xy, of a thin wire shaped along the curve C. Then the mass part of this follows from integrating this in a figure, and that's approximately this. We get a Riemann sum kind of thing. So the mass is going to be the integral of rho ds. And we can similarly, as we did before, find the center of mass of the wire with density rho this way. X bar is 1 over m. This is the integral over C. It's a line integral. And this is x times rho of xy ds. And the y is y bar is equal to 1 over m. And this is the integral over C, y rho of xy ds. And there are other interpretations that we will discuss later. So here's a problem for you. A wire takes the shape of a semicircle. X squared plus y squared equals 1 for y being bigger than or equal to 0, and is thicker near its base than near the top. Find the center of mass of the wire if, now we're saying more than just thicker, the linear density at any point on this curve is proportional to its distance from the line y equal 1. You have to think about what that means. You know what to do. Let's see how you did. Okay, so now this is proportional to the distance from 1, and it's proportional to its distance from the line y equal 1. And so at any point, the distance from the line y equal 1 is given by the density is equal to this, because you see if you go across to any one, it is going to be k, which is the proportionality constant times 1 minus y. So the mass then is going to be the integral over C of the density function. This is rho of xy. It doesn't depend on x at all. And so this is going to be and we now make the substitution to integrate that, but we're remembering that this is the semicircle, so y is going to be sine of t. So we substitute that in, and we also have the equation that you get is that we just have y. We're substituting y as sine of t. And so that is the integral from 0 to pi, because we do half of this. And we go from minus sine of t. And here we get some absolute values because it turns out that the mass is always going to be positive. And we're evaluating this from 0 to pi, and we get k times pi over 2. Now, that is going to be the mass. But y bar is going to be 1 over that mass times y. And we will get this. And when we were going over this, and remember that the parameterization along here is going to be sine squared plus cosine squared, so that's going to be 1. That's why that's not showing up here. And so this is the formula for y bar. You will integrate getting this. And again, you have to use a double angle formula to do this. Make sure you can do this because these are the kind of questions that I will ask you. So at the end of the day, the answer to this is 1 over pi minus 2, and I evaluate these at those endpoints. And so my final answer is 4 minus pi all over 2 parentheses pi minus 2. Now this is y bar, but by symmetry, because we do have symmetry associated with this, that really is going to be centered at 0, and so it's 0 comma this value, and that's approximately this if you were to use a calculator. Now, two other line integrals can be obtained, and by replacing delta s by delta x or delta y. And so these are called line integrals of f along c with respect to x and y. And when you're just going over x, it's going to be the standard kind of Riemann sum, but you have to realize that you're going over the values of c. And so what we find is that this is what we have for the x component, this is what we have for the y component. Now we want to distinguish the original line integral. They talked about the integral over c from these, and so we write them differently, and we call this the integral with respect to arc length. Now, if x is x of t and y is y of t, then dx is x prime, the derivative with respect to the dx is going to be x prime of t dt, and y is going to be this. And so what we have is the integral with respect to dx. We have x prime of t dt, and this is y prime of t dt. But realize that y equal, we have a parametric representation of x and y, and so we're using that to find x prime and y prime. And frequently, this is the way we do it then. We say this is the integral over c of, and often it will show up this way. This is p of xy dx plus q of xy dy, but the curve tells you it is a line integral. Now we're setting up a line integral, sometimes the most difficult thing, in fact I will say almost always the most difficult thing, is to think of a parametric representation for the curve whose geometric thing is given. In particular, we need to parameterize the line segment sometimes, and so a line segment would be r of t is equal to, and we're running from r0 to r1, and this is the way you can do a line segment, and there are others. So here's a problem for you to give a go. Please give this a try. Evaluate the integral over cy squared dx plus x dy, where c is a, c1, the line segment from this point, minus 5, minus 3, 2, 0, 2, and C2 is the arc of the parabola from x equal 4 minus y squared, and this goes from this point to this point. And I'm going to let you draw the picture because I've told you enough to draw the picture. You know what to do. Let's see how you did. So here's the picture that you get, and we're integrating over C1, and then we're integrating over C2. So the integral over C1 then, and this is the parameterization that you're going to get. So for that, what you need to do is this is going to be 5t minus 5, and this is going to be 5t minus 3, because when t equals 0, we're here, and when t is equal to 1, we're at 0, 2. So you have to solve to figure out what these things are, but that is a very efficient parametric representation. So this integral over c1 of y squared plus x dy is going to be, and there's what you have for x and for y, so we replace that. T is going from 0 to 1, so this is going to be y squared, and then the derivative of y with respect, this is dx, so this is going to be 5 dt, and this is going to be y, and this is dy dt, dy dt times dt, and we're going from 0 to 1. I calculate this integral, and again, I do expect you to do it, but we get minus 5 over 6. Notice we can get a negative number. Now the other one is perhaps more complicated. We're going to let x equal 4 minus y squared, and we're letting y equal y. And you could substitute t in here, but you would have t running from, and you'd have to go from 1 to something that would be a different parameterization. So the parabola is given by a function of y. This is the easiest way to parameterize it. And so we will have the integral over c2, which is this one going this way. We're going to say that this is y squared, and dx is going to be minus 2y dy plus, and then this is going to be x, which is 4 minus y squared, and then that is dy, and dy is just 1, and so we have this integral, we evaluate it, and we get 40n 5 over 6. Now the important thing is I went from this point to this point along this path and got this negative number. I went along a totally different path and I got a different number. So notice we got different answers for parts A and B. So in general, we can realize that the value of a line integral depends not just on the endpoints, but also the path, and we're also going to realize that it also depends on the orientation. Where do you start and where do you finish? And here is an important fact, but if we go along a curve C this way, we will get one answer. If we go the opposite direction, we're going to get exactly the negative of that. And it looks like there is a minus sign that's missing in this equation, but the minus sign is up here. So it's not down here in the big equation. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.